Okay, in this today presentation, I will present and discuss with you our efforts and developments towards improving both the technology and science and application of hyperspectral imaging. Over the years, hyperspectral imaging has been established, and so I don't need to do an introduction to this presentation on the basic principles of hyperspectral imaging. I think the audience is familiar with the operational concepts of this fascinating technology. It is basically acquires a stack of images across the spectrum, and then you can calculate a full spectrum per pixel. So in comparison to the RGB cameras, instead of having an RGB set of information, you have a multi-dimensional information. And because the spectra can provide analytical information, whether they are transmission or reflections or fluorescence, it is an imaging, but at the same time, it's an analytical tool. So as I said, this is an established technology in industry, and a variety of new applications are coming up all the time. However, we have come to realize that there is significant room for improvements in this field, and we are working for many years towards advancing this fascinating technology. I am Professor Kostas Ballas. I'm leading the Electronics and Photonics Department of the Department of Electrical and Computer Engineering at the Technical University of Crete in Greece, and I am also the founder of Spectricon, which is focused on developing hyperspectral imaging technologies. So I'm coming into the main body of my presentation. I'm sure that you share with me that technology is moving on by fighting against the trade-offs. You know, nature and even technology sometimes is tough enough to tell you that you cannot have them all. You have to compromise some specifications if you want to have the other specifications. So you can give up to this situation, or you can say that I can develop technologies that I can eliminate these trade-offs. And why this is important? Because there are some applications that if you don't address, if you don't sort out all of these trade-offs, you cannot enter. There are barriers to entry. For example, if you do endoscopy, you need high resolution and snapshot and video rate. If you don't do this, hyperspectral imaging cannot benefit endoscopy. Robotic vision, same thing. So I think by removing these trade-offs, new technologies, new cameras will be developed, and at the same time, new applications will come, which will open new business and new markets. So when discussing about the trade-offs, I thought that it's a good challenge to make a list on which are an ideal hyperspectral imaging. What is an ideal system? So to our view, an ideal system is that to follow the current trends on the spatial resolution in the global markets. Like, for example, you know, mobile phones now, they have like 12 megapixels. I mean, high resolution is a commodity. And it's very difficult to explain to the customers why you have like a VGA resolution. Because everybody is. So besides the marketing issue, there is a real need of hyperspectral imaging spatial resolution, because, you know, identifying fine features of the spatial domain, it adds diagnostic information. So we believe that about 4K, which is the standard of high-end medical endoscopy, resolution could be important. Spectral resolution. There is a discussion on how much, and the previous session speaker had a comment on that. How much spectral resolution do we really need? Do we need like 2 nanometers, 5 nanometers? Because if we have if we overkill the problem, and have like 2 nanometers in an application that requires 15 nanometers or a few bands, then the rest of the information will be redundant, okay? That's not, it doesn't matter. You will need to deal with this redundant information. So for example, if the application needs to do imaging, hyperspectral imaging in a plasma source, like a light source or an atmosphere or planet, then you have these sparks, the sparks that are very thin and very high. So in order for you to be able to scan and to capture this spectral information, you definitely need to have this type of spectral resolution, okay? But if you deal with solid materials, because of several absorption or emission modes are overlapping, are at the same time overlapping, the spectra are broad, are like valleys, there are mountains and valleys. And it's like in your right side image, it displays a more realistic situation of a spectrum. And if you see how many bands do I need to describe perfectly this spectrum, you will see that it's not 100 bands. It will be around 25, 30, 50, right? So that is an issue that we believe that 2 nanometers spectral resolution, it's sometimes, most of the time, is not needed. On the temporal perspective, the ideal hyperspectral imaging should have high spatial resolution, as I said, but at the same time, it should deliver the data in a high temporal resolution, meaning video rate or 50 frames per second or 100 frames per second in order to be able to monitor dynamic effects or moving objects. So snapshot should have higher spectral resolution, high spatial resolution. Spectral range, the majority of the applications are in the range between 300 nanometers and 2.2 micrometers, so the vast majority. We are doing work on the mid-infrared as well with quantum cascade lasers in developing hyperspectral images, which are active hyperspectral images. I'm not going to describe them in this presentation. Light throughput. Light throughput is very important if you want to do fast imaging. Plus, there are applications related to fluorescence in scientific or in remote sensing or detection in a variety of fields. So light throughput is very important. If your filter, the hyperspectral filter technology, cuts most of the light, you pay a significant cost in illumination. You will need to have very strong illumination, which is in most cases, if the material is sensitive, you cannot use it. Another aspect is the analysis. Most of the time, applications want to know exactly the analysis of the materials. Like, for example, to have what we call as chemical imaging. So if you train the spectra, you do a fast classification, you can identify, recognize the objects in real time. So ideally, the classification, the training process should be also in real time and not in post-processing. And operation, you don't need to have heavy devices. You need to have handheld devices to be able to go to the field. So it needs to be field deployable. So having all this in mind, we have tried to come up with a product offering that it starts with a tunable filter-based camera. So we have a new technology of tunable filters. Tunable filters have been appeared in the past working with liquid crystal systems and have a major disadvantage of not being able to be tuned in long ranges, plus they are polarization sensitive and we're sensitive in general. So we use a new technology for that, and this is a tunable filter, so we don't need scanning mechanisms. So the camera, we have a tunable filter, computer controllable electro-optic, so you don't need to have a mechanical scanner. We have a snapshot system, a family, which is of higher resolution. I'm talking about the Muse SNS product family. I'm going to say more details later on. And this is we have also a dual sensor system that goes from a silicon indium gallium arsenide sensor to cover a long range, like, for example, the cameras used in the Sentinel satellite. So the tunable filter, actually, this is the block diagram of our system. The tunable filter is, imagine that you have an interference filter that it can be changed the wavelength band that it passes through and goes to the sensor to be sensed. So this is driven and changes very fast, and the imaging sensor captures images in time sequence, and we achieve a scanning of being like about 30 seconds to fill up a scan. We achieve a very wide range of tuning, like ultraviolet to 1 micron. The camera works with 6.4 megapixels. And the benefit of this technology is that you have all the time real-time spectral imaging. You can switch in a wavelength and see real-time image. Several times it's extremely useful in applications that I'm going to share with you today. Real-time, there is no problem on resolution. It's just lens limited. If you have the right lens and the right sensor, you can get the resolution you want. And this gives the unique advantage of being portable. You can take it with you, set it up, and do hyperspectral imaging of the entire audience without moving the camera at all. As that, it adapts also to any microscope. Like, even though your microscope do not have automated scanning stages, it adapts and it provides full field, full frame spectral imaging. It is slit-free, so it has 94% light throughput, and it's suitable for fluorescence imaging. And to reconstruct the spectral cube, there is no post-processing needed because it's full frame images. There are co-registered full frame images, no post-processing to reconstruct the images. Some applications are like in artwork. You select a spectral band in the infrared, you right away see an infrared image which makes transparent and painting. There are many applications like reading old and erased manuscripts. We have collaborations with several universities worldwide, or to detect conservation activities to El Greco's paintings. In precision agriculture, you see all these vegetation indexes that are known to you, but also spectral mapping. And we also, with machine learning, we provide maps that relate to different pathologies. We use this intensively in microscopy to deconvolve multiple stains in cells. So you can apply at the same time several stains and get this spectral unmixing. So the second technology that we are developing is the snapshot technology, where we are using multiple sensors and the proprietary system to split and generate 24 images that are displayed in real time with ultra high resolution of 6.4 megapixels as well. So then we have high temporal, high spatial, and sufficient spectral information to this system, which can adapt to almost all. And this system is configurable. So the way we work is we identify the critical spectral bands in each application, and then the next step is to optimize the system. So it's configurable and reconfigurable. So we are developing a variety of applications. We have a company, QCell, which is in my group, which develops exclusively the medical. We are developing endoscopy, dermoscopy, as on the left up. With this is real time. It shows spectral mapping of dysplastic nevi, real time, and industrial uses for production line inspection, artwork, precision agriculture in the field, drone imaging, and subsea imaging. We have ROVs going with this camera to inspect the hull of the ships to detect biofouling, which is very important for taking measures of cleaning. This is in the center. It is dermoscopy that we see different nevi that have the same color appearance in the visible, but they are quite different in the hyperspectral mapping. The melanoma has this white thing, and the normal, it's just green. So this is spectral mapping in real time. This is another system that we have developed for high-throughput screening microscopy. This is I'm going to present this afternoon this technology in the Austrian Institute of Technology. Actually, this is a multisensorial system that has several hyperspectral imaging solutions, but also measures the birefringence, the optical anisotropy of transparent materials, and it is used now extensively in several labs in Europe for forensic applications. So having gone all to these features, I'm coming back now to the Spectricon's innovative product offering, and we see that we have a list of the tick boxes towards this ideal hyperspectral imaging. We do have a spatial resolution going up to 4K. We have a spectral resolution which is configurable to address specific applications, because all the applications that do not need the same spectral bands. We are working in a spectral range which is quite wide enough. Our light throughput is more than 90%, and we are video rate for the standard version, but we can go 400 frames per second in specialized sensors. We also provide real-time spectral mapping and chemical mapping if we use machine learning for that. And it is handheld and turnkey operation, including lighting and all the accessories. OK, thank you so much for your interest and your patience. And I'm here to answer questions if needed.
Are there questions concerning the tunable filter approach?
Thank you for the presentation. I have questions like you have 370 to 1070. You say 4K. You have dual sensors in there. It's the visible sensors and also sphere sensors. They have the same resolution. And how about the spectral bands? How many spectral bands there? And the other thing is like you have big data stream. How did you process in the data stream? Like you have big data, 4K, assuming that. So that's my questions. Thank you.
Thank you. So with regards to you are talking about the sensor that goes from ultraviolet to the 1.7, is that right? So we use two sensors. I mean, the spatial resolution of the silicon sensor is easy. It's given by the different manufacturers. It was difficult to find high-resolution sensors as of today. We are using indium gallium arsenide. We are now using the Sony's sensor, which goes 5 megapixels approximately. So both of them are good, but we're not going to use one. We will continue using two sensors for a variety of reasons, because we believe silicon is the best solution until 1 micron. It's even still better than the new sensor of Sony. OK? Thank you.
OK. One last question.
Hi. Do you have own interfaces to connect your camera to the drone?
To the drone, yes.
To the drone.
Yes, we do. We do. We have a camera working with the drone. I can tell you details.
But to any drone or DJI only?
Actually, we're working with two companies making drones, but the camera connects with a universal drone system. So it's not. But we work with two companies making drones. But there is not something particular. It's universal.
OK.
You know, the protocols for drones are universal.